Then we start to study energy loss of particles propagating in medium. And this is extremely important issue when we are considering detection of elementary particles. So we need to know how they interact with medium. And many things will be clear in various discoveries if you understand how electrons or protons or other particles lose the energy in the medium, and how these losses depend on parameters of particles. So I will discuss radiation energy loss, and ionization. Actually, I mentioned already ionization. Remember, we discussed discovery of neutrons, and Chadwick was using this ionization chamber. So protons actually enter this chamber, ionized medium, and then the charge, produced charge, was collected and the current was measured. So the first item, cross-section for inverse beta decay. Inverse beta decay is the process when an antineutrino interacts with proton, produces neutron and positron. This process comes from Fermi theory of weak interactions, Fermi theory for beta decay, but as outcome, as byproduct of this theory, some new processes have been predicted, and in particular this one. What I will do this lecture, and actually many times in the next lectures, I will produce for you so-called physical derivation of the result. Using some general physics arguments, so to derive exact formula for this cross-section starting from quantum field theory, I will probably need one lecture. So what I will do, I will derive it almost precisely up to coefficient of the order 1 without really using any formalism on physics ground. And this is extremely important. This actually very important when you discuss physics. So you do not use big and exact formulas when you think and discuss. You use some physics arguments, physics understanding. Then, of course, you are sitting down and making computations. But before doing computations, you need to make some estimation and to understand if there's any sense even to do these computations, because sometimes you want to find some probability and to propose some experiment, and then you compute it spanning, say, 2 weeks, 3 weeks, 1 month, and then finding probability is too small. However, you can do this doing estimations within, say, 1 hour or so. And if you find that something is really very small, then no sense even to proceed with precise computations. So what I will derive today and in future lectures are formulas essentially which as accurate as a factor of 1, probably 2, but they give also important correct dependence on physical quantities, which is also extremely important. So we deal with this process, and physics input is that I will use energies of neutrinos of the order of few MeVs. Which is typical energy of particle emitted in beta decay. That actually, this reaction has been used to discover neutrino eventually. So this means that we have energy of neutrino which is much bigger than the mass of the electron and much smaller than the mass of the proton. And we will use this circumstance. So what we have antineutrino. heating proton and producing positron and recoil neutron. So we have neutron in final state. However, for these energies, essentially recoil can be neglected. So what we are computing cross-section which is proportional to the amplitude of the process moduli squared. And here I omit for time being coefficients, which come essentially as kinematical factors, which come from integration over energy and momentum space in this process. So the amplitude is given by matrix element when I use Hamiltonian of interaction between initial and final state. And in our case, those are positron and neutron, then Hamiltonian of weak interactions, and in initial state, also neutrino, and initial state. So this is final, and initial state we have neutron. This is moduli squared. No, sorry, for this process it's not beta decay. I have final state is positron and neutron, and initial state is neutrino, antineutrino, and proton. Right, so I have to compute this element. And H is our Hamiltonian, which we derived last lecture. So this is Fermi, Hamiltonian, which was proposed by Fermi. So what is important that this Hamiltonian is proportional to G Fermi. And therefore the cross-section should be proportional to G Fermi squared. Okay? So that we are writing that sigma is proportional to G Fermi squared. So now let us use dimensional argument. Which is extremely important in many derivations. I will probably do it here. So cross-section has dimension centimeter square or mass minus 2. G Fermi has dimension mass minus 2, and square is mass to the minus 4. And therefore cross-section should be G Fermi squared multiplied by some quantity, and this quantity has dimension mass squared, right? So it's dimension of mass or energy squared. What are parameters of mass or energy in the problem? So those are mass of electron, positron, energy of neutrino, mass of the proton. So those are parameters of dimension energy. So somehow this x should be cooked out of this parameter.
Why not mass of the neutron?
Yeah, so this is what I want to add. Also mass of the neutron. In the first approximation you can say that they are the same. So we proceed in the following way. So what we are saying that the energy of neutrino is much smaller than the mass of the proton. So which means that I can neglect recoil. I think you will have exercise at some point to estimate what is the recoil energy. And therefore, in the first approximation, I can use mass of the proton, essentially infinity. It's very heavy. The energy of neutrino is at least 100 times smaller than the mass of the proton, the neutron, and therefore this is very heavy body for these neutrinos and for this scattering. And in the first approximation, I can put this as infinity. So that actually is not important in the first approximation. Another point is that the energy of neutrino is much bigger than the mass of the electron. And therefore I can neglect the mass of the electron, again in the first approximation. Then I can introduce corrections. And therefore the only parameter of the dimension energy is the neutrino energy. So then X should be energy squared. And therefore we get expression for the cross section, which is G Fermi square energy of neutrino square. Well, in fact, this is very close to what we have as a result of exact computations. Now let me write the formula. Sigma is G Fermi squared. Now instead of energy, actually what is written is momentum of electron and the energy of electron. And in approximation, when I can neglect nu E, this is essentially energy of neutrino, this is energy of neutrino, and I have here energy of neutrino. And that should be multiplied by the following factor, 1 plus 3 GA squared over pi. So this is the result of exact computations in the lowest order. So that is approximately energy of neutrino squared. If you neglect difference, and that will explain what we neglect actually a little bit more. So you see, our very quick derivation actually is very close to exact result. This factor is 4 over 3. So that the difference between that and this formula is essentially a factor of 4 over 3, or 30% of. I know that many of you are unsatisfactory. Say, okay, so what is kind of hand-waving arguments now? But it's a really very serious physics argument. Because what this formula gives, or this one, is that cross-section increases with energy, a square. And this is very typical in the case of scattering due to very short range interactions. Remember we discussed that the interaction is very short. It's, as you know now, inverse of mass of the W boson. And if you have very long wave, which is given by 1 over P, then the result of scattering is very small. So result of the scattering, and we can use wave picture, is the distortion of waves. So in wave picture you need to compute how the wave is distorted when you have scattering on some very small object. Okay? Now, if the wave becomes smaller and smaller, the distortion will be bigger. And of course, if wave becomes comparable with the size of your object, then distortion is very big. So then one expects that the bigger energy, the shorter is wave, the stronger is interaction. And this is what you see in this formula. Now, what is staying here is momentum and the energy of electron. And the point is that this process has threshold. And this is because mass difference between neutron and proton. And so in the exercise you need to compute what is this threshold. It's of the order of 1 MeV actually. So it's the difference of masses, roughly, of masses of neutron and mass of the proton. Neutron is a bit heavier than proton, and therefore with very small neutrino energy you cannot proceed with this reaction. And also you will need to produce what? You need to produce also for the positron in final state. Okay? So you need to subtract in the first approximation is also the mass of the positron. So this is taken into account in the factor P and energy here. So I need to subtract from the energy the threshold. Let me make again general comment on this type of the derivation. Standard way in quantum field theory is that you start with Hamiltonian or Lagrangian, right? Hamiltonian interactions. Then you do QFT computations, knowing the rules of these computations. And finally, you find observables. And observables are cross sections, probabilities, or decay rates. But what is important that these observables are functions of kinematical variables. So all these, like for instance cross section, is the function of moment or energy of particles involved and spins. Right? And coupling constants. Let me add here G coupling constants. So you do all this kind of machinery and computations, but eventually you find some function of variables. So you have the process, and you have some external particles with spin. Let me put S here, with spins and momenta, and eventually your probabilities or cross sections are the functions of these external variables, kinematical variables. So what we are doing, we are jumping immediately without all this kind of machinery to the answer using this physics derivation. So using physics arguments, you can find these functions of variables. And what we are using here is kinematics. We use here symmetries often. We use Lorentz invariance, of course. And dimensional arguments. So, using all these, you can actually find what is this sigma without doing these exact computations, up to, say, numerical coefficients. Up to numerical coefficients, using these things, you can find the final answer. By the way, even in this formula, I can find what should be the power of pi here. It depends just on number of particles in final state. So just this pi can be identified what should be the power. In this case, it's pi in the first power in denominator. But knowing how many particles are in final and initial state, I can find what should be the pi. Now, this is contribution from, remember, axial vector current. We will discuss this later. So this G, A, is approximately 1.23 for this transition. And factor of 3 is related to total spin in the process, because we have antineutrino interacting with say, U quark, right? We are at the quark level. And in this system, and knowing that interactions are B minus A, we haven't studied yet this, but I'm saying that these days one can proceed much further than just this. Total spin in the system of antineutrino and U quark is 1. And the 3 is related just to total number of possible projections of the spin. Okay. So this is also kinematics, right? So which means that just using kinematics arguments, we can proceed very far in computing of what we want to have finally. This type of approach actually has further developments quite recently. Maybe you heard this, maybe not. So people really developed this approach, amplitudes, which is called amplitudes. And the basic idea is the same, how to find the final answer using usual kinematical, standard kinematical arguments and some symmetries in the problem. I will show you some other examples of this type. Questions?
What kind of problems are being addressed right now with this method?
Oh, so people are computing some amplitudes of in QCD, for instance. Anything, you can use anything. So people are using general stuff that suppose we have some model, QFT model with fermions, with bosons, with some masses, and then you get some general expressions for the amplitudes, or probabilities eventually. Take this seriously. That is very helpful, believe me. You will appreciate, maybe not now, but later. So once you do this exact computation, spend a lot of time, getting some result, but then the result turns out to be wrong, and okay, you redo this again. But this is what I'm doing in the first place, do estimation, before I start to do some spending more time on various things. And again, when we are discussing physics with colleagues, we are not using these very precise formulas, but we kind of think in these terms. Simple. This you can remember or immediately reproduce. So when we are discussing, we are not running immediately to library to see some books or opening internet and looking for what is even there. Okay?
So from this expression you could find some experimental value for GA, right?
Sorry, what?
From this expression of the cross-section you could find the experimental value for GA.
If you want, but it was found from decay rates, as I discussed before, and already known value of GF was used to make a cross-section estimations. So you will have an exercise, you will see, and so what we are discussing now, the first estimations has been done by Hansbeth and Piles. And the conclusion was that almost hopeless to detect neutrinos because cross-section is too small, at least at low energies. And cross-section increases. And actually the behavior of cross-section changes with energy when the wavelength becomes comparable with the radius of interactions. And cross-sections stop to increase, becomes constant. Well, at least in scattering on point-like objects. Then one is also to take into account that protons and neutrons are composed of quarks. So So then you start already probe at energies comparable with the mass of the W boson mediator of the interaction. So in this case, you already start to probe the structure, or even before structure of nucleon. You start to probe the structure of nucleon when the energy becomes bigger or much bigger than the mass of the proton and neutron.
Is that the meaning of weak interaction energy scale?
Sorry?
Is that the meaning of weak interaction energy scale?
So this is, so that determines the radius of weak interactions. Weak interactions, this is also weak interaction. The cross-section behavior is like this. It increases linearly, so then it would be like this if proton and neutron would be the point-like. However, due to structure or quark structure pattern, actually increase continuous but not as fast as linear. So not like quadratic. Let me correct a little bit more. Actually, the deviation will be even before this. So what we have is this quadratic behavior. Then at energies which are comparable with the mass of the proton, it becomes linear, and then it stops. So this is general formula. On the point-like. If this is not point-like, then it will increase like that. So this is complete picture. Quadratic, when the energy of neutrino is much smaller than the mass of the proton, of the target. Then it becomes linear. And this is when it is comparable with the mass of the W boson. Behavior changes again. But we are here, so, in this consideration, this range. Actually, you can also derive cross-section in the case when neutrino energy is bigger than the mass of the proton and get this linear dependence. Also using dimensional arguments. Because when you have energy of neutrino comparable with the mass of the proton, then another mass parameter, or an energy parameter, is involved. The mass of the proton or neutron. There are some exceptional cases when this simple dimensional argument doesn't work, and I will show you this when we will discuss decay of pions. So in various exercises, you will derive number of events. So let me tell you a little bit more about this, how you compute number of events. In your detector. So suppose you have flux of neutrinos, once we discuss neutrinos, which hits the detector. And for simplicity, we'll consider the detector of this form, and it has area here S, and the length L, and density N. Suppose the flux of incoming particle is F, so it's actually density of flux. Which is number of incoming particle which cross unit of surface. So let me write it here. F is number of, in our case, neutrinos which cross unit of surface in unit of time. so that the dimension of F is centimeter squared in denominator second. F times S gives us total flux. If flux is uniform, otherwise you need to make integration. So if flux is uniform, that produces a total flux of neutrinos which enter the detector. So important notion is rate of events in detector. And rate of the events is number of events, total number of events, or over time, and T is exposure time. So we will work in approximation when the probability of interaction of individual particle inside this volume is much smaller than 1, which is certainly satisfied for neutrinos. If this is not the case, then one needs to consider small layers and repeat what I'm doing within small layers, take into account absorption of the flux, and then make integration over the volume. So, in this approximation, the rate can be written as the probability of interaction of individual neutrino multiplied by the flux, by total flux. So again, P is the probability of interaction of individual neutrino. And this is total flux. And total flux is number of neutrinos entering our detector per second. And therefore, this automatically gives for us the rate of the process, rate of interactions and production of a given event. Okay? So now let us write an explicit expression for this P, which we have derived last lecture. And this P is, let me write immediately. The rate is, I'm writing sigma times n times L. This is what we had for probability. And then multiplying by density of the flux and time S. Agree? Now what is staying here is the following. L times S is nothing but volume of the detector. Okay? Multiplied by n gives us total number of particles. So n times V. Detector gives us total number of particles in the detector. Tag. So let me use for this notation. This is total number of particles. And therefore, we can write the rate as cross-section times total number of particles and times the density of the flux. And of course, if you want to compute number of events produced in this way during some time t, then you need to multiply this by the time, exposure time. Then you will get total number of events produced during the time t. Okay? So you will have exercise, and you will need this to use in your exercise when you compute number of events. I don't, maybe not in this exercise, but the next set of the exercises when you compute number of events produced by neutrino in the detector. Questions?
Okay, maybe not the class, but this set of the exercises for the next Friday?
Yes.
Okay.
I said already this.
The large N here is the number of targets in the...
Yeah, number of particles in the detector. So everything is clear? Good. So now we will discuss, so next topic is interaction of particles with medium. So this is important to understand how we really detect particles and how we get information about properties of the particles. We do not see the particles themselves. What we see is the secondary effects produced by particles in medium very often. So most of the discoveries are based on detection of secondary effects of propagation of particles in medium. And what is important, particles produce some tracks in medium. And so we observe these tracks and we measure the properties of these tracks. We apply electric or magnetic field trying to manipulate with particles, see how the tracks are changing, and in this way we are getting information about properties of particles. Clearly that observable effect is proportional to energy loss. The bigger the energy loss, the bigger effect, secondary one, right? So it's proportional to energy loss in unit of distance. This is important characteristic of interaction. And we quantify this by dE over dx. And usually measure this in the units MeV over centimeter. Energy loss on the unit of length. So this is important quantity which we are using in description of particles. So what happens if, for instance, electron or proton enter iron, so layer of iron, or lead, or maybe some nitrogen or some gas? So what are the processes? Tell me, what do you know? So what will happen with proton or electron when it enters medium? Yeah. So one of the processes is ionization. Of course, if it is charged particle, right? So if a proton and electron, yes, so they will ionize particle. What else?
Neutron capture. Neutron capture.
Well, they can be captured, yes. But then they will not produce tracks, so they just capture, they disappear. So what other processes which can be?
If they are high energy, then they can knock off other particles from the medium.
Well, this is the same ionization. So ionization, when you have they knock the electrons from atoms.
But it can happen that the the particles which are produced by ionization remain in the medium, or they can go out of the medium.
Yes, like in photo effect, you knock electron out of medium. Yes, it can be, but the original process is ionization. So what?
Particle is charged, you don't have Cherenkov radiation.
Right. So what you are saying correctly. So Cherenkov radiation, which is an important process. And just simply radiation, right? Radiation energy loss. Oh, radiation, once we start to work. So what is interesting that Cherenkov radiation is not very important for energy loss, but it's very important for detection of particles. But mostly what we will discuss is this ionization and radiation. This is what people use actually to detect particles. These are the processes which produce eventually the tracks or influence the properties of the tracks. And I will start with radiation. So the process is like this. In medium you have electrons and nuclei, charged particles, and then when you have incoming particle, let me denote it as L, what it does, it interacts with electric field produced by particles of medium, and then they emit itself photon. So it also can emit from initial state. Again, so some of you haven't seen Feynman diagrams. So for time being, you can just see this as a cartoon, which shows what's going on. You have initial particle, for instance. You have nuclei, or you have electron. In atom, you have both. And then there is this type of the process. They exchange a given particle with nuclei by exchange of photon, and then emits the photon itself. So the process is like you have electron plus nuclei, which is composed of a number of nucleons, and this is Z, it's the charge of the nuclei. And in final state you have this electron or lepton, whatever it is, plus Z A and plus gamma. This is the process. And of course particle loses the energy because it emits gamma. So after integration over photons, if you want to have total energy loss, because in different collisions you will have different emission of gammas with different energies. When after you do integration over everything, then it's clear that the only dimensional parameter is the energy of particle itself, incoming particle, and therefore the energy loss is proportional to the energy of particle itself. And again, on dimensional ground, you can write that dE L over dx equals the energy of particle over L, some parameter, some distance, to get correct dimension. And this parameter is called radiation length. So, if radiation length doesn't depend on energy of neutrino, then this equation can be easily integrated. I have forgotten minus sign here because the energy decreases. And the integration is trivial. I will get exponent, right? I will get EL, which is equal EL0, and then exponent minus X over LR. So again, if radiation length doesn't depend on energy, and we will see that in most of the cases, this is what is realized, then what will happen is exponential decrease of energy of particle when it emits photons. So, and the sense of radiation length is the length over which the energy decreases by 2.7, by E. Okay? So now let us consider in more details radiation length, how to compute it. So this is kind of empirical expression, but in reality we are computing dE over dx, which is minus, this is average energy loss in a single collision, multiplied by sigma n, and this is the target number of atoms, and this is the probability of collision over 1 unit of length. Okay. So then this dE over dx, the energy loss is the average energy loss in a single collision, and this gives you a number of collisions within 1 unit of length. Okay? So this is average energy loss is proportional to energy of particle itself with some coefficient. And therefore 1 over L radiated, if we compare these two expressions, is sigma and A, and multiple, okay, so it's enough for sake, because this is proportional, so of course the average is slightly smaller than the energy of particle. So this is density of atoms. And this is cross section. So, how cross-section looks like? Cross-section, and I will give final formula. I don't want to present the derivation. It's kind of lengthy thing. And then explain different factors in this formula. The cross-section is given by 4 alpha cube, and this is fine structure coming from. This is 1 over 137, and this is because we had, remember, diagram of this type. So there are 3 points where we have electromagnetic interactions, here, here, and there. And therefore, the amplitude is proportional to E cubed. And when we compute probability, we square this, and therefore we will have this alpha, all right, which is E squared over 4 pi. other factors are the following. M L square Z plus 1 and logarithm 1A3, and here it will be Z1/3. And this is so-called screening factor. So if you want to compute dE over dx, you need to multiply this by energy and number density of atoms. According to what is written there. So the most important parameters and factors are here. There's this one, and this one. So this is electric charge of the nuclei. So I explained already this factor of Q. Now this you can find just because of dimension, right? This is cross-section, it should be 1 over mass squared, and the only mass which actually has dynamical feature is the mass of the particle itself. If particle is much lighter, the nuclei themselves. So this means that nuclei is just staying and has almost infinite mass, and therefore dynamical variable is the mass of the particle. And this is extremely important characteristic because the lighter the particle, the bigger cross-section. So what I will do, I will explain.
Why not the total energy of the particle? I just assuming that is stationary when it's...
Well, I made so the energy of the particle is staying here.
Yes. Okay.
So when I compute dE over dx, and here there is no energy. So this way actually radiation length doesn't depend on energy of the particle.
Because the dependency is in the Earth?
Well, dependence is when you do this dE over dx. It depends on mass, and so that's computation when we integrate over energies, loss of the energy of gamma, which appears here. Then we get this result.
Okay.
So you see, so here is average energy of energy loss, average energy of gamma emitted. So that already kind of implies some integration. So you need to have integration here. But the rest doesn't depend on energy. Yeah.
This screening factor is purely empirical.
So this is actually what is saying here is critical charge, because there are some derivations of this parameter. And Z1/3 is the number of nucleons or charges when the particle is in one dimension, right? So that's why it's 1/3. Now this formula is valid for momentum transfer in the range from 10 to the minus 13 centimeters to 10 to the minus 8 centimeters. So in this range. Outside of this range, the formula should be modified. So now let me explain the factors which appear in this formula. And the first I want to explain is 1 over the mass of this incoming particle. Again, the lighter the particle, the more efficient is radiation. And it has very clear classical analogy. So suppose you have nuclei with charged particle, and another one is passing through and radiates. The lighter the particle, the easier it deviates. So it has bigger acceleration. The smaller the mass of the particle, the bigger is acceleration or deceleration, and therefore the bigger is radiation. Radiation is proportional at classical level to acceleration or deceleration of particles. So the force in this case is the charge squared over the radius squared. So acceleration is F over the mass of the particle, right? This means that this is E square R square 1 over the mass of the particle. And so radiation is proportional to acceleration in classical analysis. If you go to quantum situation, then you need to square this, and therefore radiation is proportional in the quantum case. It's A squared, which is inversely proportional then to ml squared. So this is the origin of this factor, that kind of physics explanation. Again, the lighter the particle, the stronger it accelerates in a given field, or change the velocity or change the momentum, and therefore the more it radiates. Okay? So this is important. You may not remember all these kind of coefficients, the factor of 4, or even this screening factor, but what is important that you should remember that radiation energy loss is inversely proportional to the mass of the particle squared. So the electron will radiate much more than proton, which is much heavier particle. So in the same field, proton will have a weaker change of the momentum, and therefore it radiates less. Substantially less, you see, its mass is squared, which means that it's 6 orders of magnitude smaller radiation. Already you have some idea, right? If you're proton or electron entering the medium, then electron can lose the energy by radiation, but proton will do something else. So let me give you some example that for instance, for electron, in lead, radiation length is 0.56 centimeters. So if you want to shield yourself, right, from radiation produced by electron, then you need to take lead and a few centimeters, and then the flux of electron and radiation, flux of the electron will be suppressed very strongly because they will lose the energy. Okay? And you will again have the exercises to play with this energy loss.
Your calculation is saying that that if we have an electron, then it will lose energy by radiation much quicker than the proton.
Yeah.
But if we do the experiment in the real world, we should consider the fact that we are not considering ionization here. We are only considering radiation.
Only radiation for time being. So now we are coming to ionization.
It doesn't mean that in the real world experiment, electron will have a shorter range because we're not taking all of the factors into account.
Yeah, sure. One needs to take into account ionization, and I will make a comparison with proton energy, and you will have also exercises on that. Now, what is this factor? Can you guess what is this? What is the origin of this factor? Which is also very important, right? So what is this? Okay, I can write it as z squared plus z. Does it help?
But if it was that square, it was easier to guess.
So what is this?
Because it's that the particle can have a charge of z times. So
No, this is z is the charge of nuclei.
oh, okay.
Okay, so yeah.
So
So what you have atoms, right? This is z, which gives you also the number of electrons, right? So if you're neutral atoms, the particle crosses the medium with these atoms. So this factor appears in radiation energy loss.
what is the charge of the particle who's losing the energy?
Well, so that enters here, and this formula is when a particle has a unit, just like the electron. Of course, if you have bigger charge, then it should be multiplied here. It should be then Q if particle square if, for a given particle. So let us assume this is single charged particle chambers. So what is this factor is the following. This one corresponds to scattering on nuclei, and this is due to scattering on electrons. In a given atom. And this is valid only in this range of inverse of momenta, which actually corresponds to the range from keV momenta up to, so that's 100 MeVs, which is for many experiments is the most important range. So that corresponds to Q itself in this range. So then why it is different? There is a difference between scattering on electrons and nuclei. Any guess? This is because in such a range of momenta, scattering on nuclei proceeds as coherent scattering. Coherent scattering on protons in a given nuclei. So we have nuclei, the charge is Z, which means that we have Z protons in our nuclei. And here we deal with coherent scattering. Do you know what does it mean, coherent scattering? And in the case of electrons, scattering is incoherent. I will use this occasion to explain what is coherent, what is incoherent, and this is extremely important stuff, and we will meet this in many cases in the future. So what is coherent and what is not coherent? So this is next topic, coherence. Suppose we have some object of the size of radius d filled in by particles, like nuclei is filled by protons. And we have wave which actually falls onto this object, And this wave scatters on different elements. And then somewhere here we see the result of the scattering. So this is our detector here. And we see the result of scattering on different components of our object. So we are computing the probability of scattering, and it is given by the sum over these objects of the amplitudes of scattering on individual objects. So this is general expression for the probability. So we find probability, the amplitude of scattering on individual elements here, and I can introduce here, say, R I, the radius here, coordinate, and so I need finally to find this moduli square of the sum. So how it is written? Let us open the sum, and it's given by moduli square of each of these elements, each amplitudes, plus what we call interference between different amplitudes, plus 2, that's sum, ij, fi minus fj. So each of the amplitudes can be written as moduli of the amplitude and phase. But I think you will not confuse. This is I, and I index. Probably better to use J. Okay? Now, these R describes coordinate inside the body, and the distance from a given element to our detector, let me denote it as xi. Then the phase, which is argument of the amplitude, is given by y momentum times x. And let me consider that momentum is the same for all the scatterers. Then it will be given just by p times xi. Okay? Now let me come back to this expression. So do you understand what's going on? So this is when I'm opening this, I'm getting, these are cross terms, right, when I do square, and so these are moduli of individual amplitude square. Okay, and then I have these exponents with plus and minus sign, which gives me cosine and factor of 2. I don't want to repeat, but you please do this for 2 amplitudes, and then you will understand immediately what's going on. So we have here the difference of the amplitudes, difference of the phases of the waves, scattered waves, which arrive from different scatterers inside. Right? So that's what is the phase. Since these particles are in different places, the x is different, but it's different by the size of this body itself. And therefore you have this additional phase difference. Now this first term corresponds to what we call incoherent scattering. And this is interference. So let us consider two cases. The first is when D is, let me add another formula. So let me add the formula for difference of the phases, which is Fi minus Fj, which appear here. And it will be given by 2 pi over lambda. And here is xi minus xj, right? And this is nothing but p, right? Which we are using here. So difference of the phases will be equal to difference of distances over the times momentum, or 2 pi over lambda. Okay. So the first case, when d is much smaller than lambda, d is the size of the object. This is d. When d is much smaller than lambda, then the difference of the phases is much smaller than 1. So, in this case, these cosines are just 1, right? Because difference is very small, difference of the phases. And so what we have, that the probability is just given by this first term and this interference term without cosine, and it can be written as sum I n moduli square, so I and then square. Well, this can be obtained immediately from this expression, and the point is that if this all the amplitudes, so the phase differences are not important, then we just remove these phases and then can use that this is I moduli. If difference of the phases is not important, then we just the absolute values of the phases. So if I have the same number, the number of scatterers n, and the same amplitude for all the scatterers, then this probability will be proportional to n squared. Right. So that will be n times a square, and so it will be proportional to n squared. Right? Ask me questions. No, don't. So again, if phase difference is very small, if you want, I can put out the phase because all the terms will have the same phase. I can put it out. And so what is left is essentially moduli, sum of the moduli, absolute values of the phases, of the amplitudes.
And this is the case for the nuclei because they are so small. We will have a contribution of z square because it is n square.
Yeah, so that's the conclusion. So if you have coherent scattering, and our scatterers are protons inside the nuclei, and therefore in the case of coherent scattering, the effect should be proportional to z squared. Now the second case, when d is much bigger than lambda, then the phase difference is big. And therefore, these terms will have different phases and it will cancel, substantially reduced. So then what is left is just the first term. So in this case, sorry, I want to write this more carefully. But I need this, right? That's our expressions for the phase difference. So in such a situation, I have phases or phase differences, delta f, which is much bigger than 2 pi, and they randomly change. And in this case, the p will be given by the sum of the amplitudes squared. So, which means in this case, if the amplitudes are the same, I will get n multiplied by a moduli squared. So, in such a situation, the effect will be proportional to n, to number of scatters, not n squared. Okay?
So we can say that in the coherent scattering, the wave which scatters from every scattering site has the same phase shift.
Yeah.
Because the phase differences are given.
Yeah, because the difference is small. So the difference between, and this is because distances are much smaller than wavelengths, and therefore you can neglect this difference, and you will get, we can put out the phase. I can do this in more careful saying that in the coherent case, this is given by sum, and I will write here amplitude I, and here is E I phi I over, and this is moduli square. And then, since all the phases are approximately the same, I can put it out. So that will be exponent I phi. I neglect difference between phases, and here it will be sum of I, the amplitude, I moduli the square. So that is in the case of coherence. And the phases, difference of the phases is neglected, and then it just can be removed. And I'm getting the expression in the case of coherence. Okay? So coming back to our exercise with radiation energy loss, we have the following scatterers. We have protons in nuclei, and we have electrons. So the situation in our case, in radiation case, we have atom with electrons and nuclei. And in the range which I have mentioned, the wavelength is somewhere in between the size of the nuclei, so this is lambda, and the size of the atom. Therefore, since this wavelength is much bigger than the size of the nuclei, the scattering on protons inside the nuclei is coherent. Is coherent, but scattering on electrons is incoherent because the wavelength is much smaller than the size of the atom, and therefore it's much smaller than the distance between electrons inside the atom, and therefore scattering on electrons inside an atom will be incoherent. And so this is this is the origin, so that will give Z squared, and so scattering on electrons. Incoherent. And so it gives Z.
You said that the formula of the cross-section that you wrote, it has a lower bound for the energy of the incoming particle.
Yeah.
And it comes from the fact that because if the particle has too low energy, then the scattering from the electrons too might get incoherent.
Yeah, so what's interesting, this is the question which I wanted to ask you first. Suppose now the wavelength is bigger than the size of the atom, which means that the energy or momentum of incoming particle is small. So what will happen in this case?
Then the electron and scattering will become
And
incoherent.
the situation even worse, because if that particle will see atom as a whole, which is neutral. It's not only you. So the scattering will die very quickly because of neutrality of atom. So with these big wavelengths, everything will be coherent if you want. But since you have different charges for electron and proton, they will cancel each other.
So from this learning, we can also work out the formula. If we have a very low energy particle scattering from an ion, it's kind of like a coherent scattering from a nucleus of charge 1.
Or charge 0. Right?
Yeah.
So in the case of very big lengths, in our sum, I will need to sum both on protons and electrons in atom. So what I will need to sum, let me put here electrons, plus sum of the amplitudes on the protons. And since they have different charges, opposite charges, these amplitudes will cancel.
I'm saying that suppose that there is a very low energy particle that is scattering from an ion. So
Oh, if you have ion, of course, then it will be some scattering.
then it is the kind of same as if we are considering a not so low energy particle but scattering from a nucleus. So it's kind of like the same. Because the ion will have the same charge as the nucleus. If we have the effective charge of the nucleus.
Or if you have system of nuclei, yes, then you need to take into account the distance between nuclei, different nuclei. So that's a different scale, right? It's even bigger than the atomic scale. Well, now my question is, what is more important probably if my P is much bigger than this 100 MeVs, what will happen? In this case, so this opposite case, when we have very small wavelengths of big momentum of incoming particles. So what will happen in this case?
The nuclear scattering will be incoherent.
Right, so then the Z square dependence will be destroyed. Then it will be incoherent scattering. And actually very soon you need also to take into account the scattering even on quarks. Because if you go further, say, the momentum bigger than 1 GeV, then you already need to consider the scattering on individual quarks and then somehow. But Z square dependence disappears for these high energies. More questions? So, the fundamentals of this coherent scattering means that if you have system of scatterers, the coherence is realized when the phase difference due to scattering on different scatterers is small, or negligibly small, and therefore, so they are close enough. And so the distance between scatterers is smaller, much smaller than the wavelengths of your incoming particle. Then the scattering is coherent. If the wavelength is smaller than the distance between the particles, then you can resolve different particles in your system. Again, the same story with microscope, if you want. You see, that appears everywhere. So let me the secret is that actually there's diversity in nature. However, at certain level, at fundamental level, many things are the same, it's just different realizations of the same thing. So if you understand, actually you need to understand not too many things and then apply it to different systems. And this coherence will appear again in many, many places. So for instance, a few years ago, for the first time, coherent scattering of neutrinos on nuclei have been detected. So for charged particle, this is routine. But just for a few years ago, for the first time, scattering of neutrinos on nuclei, the coherent scattering has been detected. That can lead to very important developments, because then for detection you do not need very big detectors. As usually for neutrinos, you need huge detectors to collect a number of events. However, if you have enhancement due to this coherent factor, then your size of your detector can be much smaller.
In this coherent detection, the mediator is in Z boson? Or
Z boson, yeah, so it's Z boson. More questions? So we'll start ionizations, to study ionization next lecture. Okay.
I didn't hear the sheet.
Ah.